Okay, let's look at some examples from the 3.4 homework. And I'm going to start with number 2. Number 2 obviously is talking about half-life. So we have a particular radioactive element whose half-life is 14 minutes. What does that mean? Remind me what that means. That means that it takes 14 minutes before this radioactive element has decayed by half of its amount. So it's left with half of what it started with after 14 minutes. And what we're going to look for is, okay, what's the decay rate for that element if its half-life is 14 minutes? Now, there's a couple of different ways I could go about this. First of all, we have a formula for half-life. The time it takes for a certain object or item to reach half of its value is equal to the natural log of 1/2 divided by whatever that decay rate. And so in our example, we know this value. We know the time it takes for it to reach half its value. So I can plug that in for t of 1/2, and I get 14 is equal to the natural log of 1/2 over k. And I could solve from there. So multiply both sides by k, I'm left with 14k equals natural log of 1/2, and then divide by 14. And I get k is equal to the natural log of 1/2 over 14. When I plug that into my calculator, I get negative 0.04951, and that should be enough decimal places, so I'll stop there. But notice, I want to point some things out. First of all, it's negative. Is that okay? Well, of course that's okay, because this is a decay rate. It should be negative. The fact that it's negative means it's decaying. So the negative's okay, and remember, I want this as a percentage, so I need to move the decimal place over 2 times before I round. So I get 4.951%, and then I'm going to round that to the nearest tenth. Well, here's my tenth spot, so I'm going to look at that number, and that tells me to round up, so I get 5.0%. So that's one way I could solve it, and that's if you remember my half-life formula, but I can also solve this just thinking about it as an exponential function, right? Since this is exponential, I can write it in my normal exponential form. And then knowing what I know about half-life, I can set this up to where I can solve for that rate in this way. If I'm looking for the half-life of this element, then I'm looking for where my output value is half of what I've started with, right? 1/2 of n naught, or n sub 0. But I already know how long that's going to take. That's going to take 14 minutes, so I can plug 14 in for t. And then I can solve from there. I can divide by n naught, and notice what happens. Once again, just like with doubling time, that initial value cancels out. How do I get 14k out of the exponent? I take the natural log of both sides. So I get natural log of 1/2 equals the natural log and the e are going to cancel out. And notice what I'm left with. I'm left with the same exact thing as I have over here. And so I end up getting the same exact thing. But that's really where that half-life formula comes from. It comes from just setting it up like an exponential function and then solving for k, or solving for t. So when I finish dividing, I'm going to get that same thing of negative 5% after I round it, right? Now careful, if you plug it in as a negative, I think it'll actually mark you wrong. And that's because the problem already states that it's a decay rate. And so because it's already telling you it's decay rate, you don't need to include the negative with your answer. The negative's implied because we're already saying it's a decay rate. Okay, let's look at number 6. So this one, the sales of a product have declined in recent years. Aha! That word declined is a good hint that this is going to be decay, right? We're working with exponential decay because our values are going down. They were 201 million in 1984 and 1.4 million sold in 1994. Assume the sales are decreasing according to an exponential decay model. So we're assuming exponential decay, and notice how it writes it here. It includes that negative in there because that's how we can for sure know that this is decay, is because we're for sure going to have a negative in the exponent. And let's go through these 3 steps. First, let's find that decay rate. Let's find that value k and write my exponential function that models this situation. So how am I going to do this? Well, the way I'm going to do this is I'm given two different data points. I'm given the amount that were sold in 1984, and I'm given the amount that were sold in 1994. So that's how I'm gonna actually complete this problem. And the other key thing that's going to be helpful here is recognizing that T is going to represent years since 1984. So if I assume that with my T value, that means I'm starting at 1984. That's my starting point. In that case, what is S naught? S naught is going to be my starting value, what I'm actually starting at. So S naught is that 201 million. And a couple of different ways you can go about this. You can create your equation in terms of millions, or you can convert everything. I can add on the extra 6 zeros if I wanted, and then it's in terms of just regular amounts. It will come into play. You need to make sure and stay consistent as we go throughout this problem, because in part C, things get a little tricky with this. Since I've already changed this, I've already added the extra zeros, I'm gonna just keep it in terms of just products, not millions of products, but just products. And then I have e to the negative kt. Okay, so now I have my starting value in my function. But now what? All I'm missing is that decay rate. So how am I supposed to find the decay rate? I use my next data point. I know that in 1994, it's decreased to 1.4 million. Well, first of all, how many years is that? From 1984 to 1994? That is 10 years. And that's what my T value is going to represent. 10 years have passed from when this started. I can plug 10 in for T. But what do I know about after 10 years? After 10 years, I know the amount that were sold. So I have my corresponding output value. So that 1.4 million is going to go right here. Remember, if this number is in terms of millions, to get it in terms of just regular products, I move that decimal place over 6 times. So I get 1,400,000 products. And now I have an equation with only one variable. And so therefore I can solve for that variable. So I'm going to go ahead and do that. First, I'm going to divide by 201 million. When I do that, the 201 millions on the right side cancel out, and I'm just left with either negative 10k. And on the left side, I get 0.0069651741. I'm going to keep as many decimal places as possible. Remember, I don't want to round until the very end. Now what? Well, now I'm at this point where I need to get this out of the exponent, so I'm going to take the natural log of both sides. And I'm left with, remember, over here, the natural log and the e cancel out, so I'm left with negative 10k equals this natural log of 0.0069651741. I can go ahead and plug that into my calculator right now if I want to and get another really long value. Regardless, I should get about negative 4.96683266714 equals negative 10k. Last step is just to divide by negative 10. And this is where I'll go ahead and round. It tells you to round to 6 decimal places. And so I get negative 0.49663. Oh, and the negatives canceled out. And that's because there was already a negative in the formula. And so it's okay that k is positive because there's already a negative in the formula. So there's my k value, and that lets me rewrite my function as 201 million. Remember, I'm writing out all the zeros, and you'll see why in just a little bit. Times e to the negative. The negative was part of the formula. And then here's my k value. And that's multiplied by t. Very nice. So there's my formula. And so now let's move on. Part B says to estimate the sales of the product in the year 2002. That means I'm solving for my sales. So I'm solving for S. That's what I'm trying to figure out. And I'm given a value of T. I'm given 2002 as the year that I'm looking at. Okay, well, if I'm looking at 2002, what's my T value? How many years is that since 1984? Well, you can use subtraction, but you get 18 years. So that tells me what to plug in for T. Part B, you're just plugging 18 in for T. Then from here, it's just all calculation. And I get 26,331.5064, yada, yada, yada. But I think this one asks you to round to the nearest whole. So if I look at my next value after the decimal place, that means I'm going to round up. And so I have about 26,332 units. And honestly, here in part B, we're already seeing the benefit of not writing the numbers in terms of millions, but actually writing the numbers out. Because then when we got this result, it wasn't 0.00 something. It was just already in terms of thousands. Okay, last, part C. And this is why I wanted to do this problem, because this one can be a little tricky. In what year, theoretically, because this probably won't actually happen, but in what year will only one product be sold? So notice what's given to us and what we have to figure out. We're given sales. That one represents the amount that's sold, and what are we solving for? We're solving for time. We don't know how many years have passed. So I'm going to come back down to my equation. So I'm back to using this equation right here. But now I have different things to plug in. I know my ending sales value. I want my ending sales values to be just 1. And I'm going to set that equal to 201 million e to the negative 0.496683 multiplied by t. I don't know how long this is going to take. And so I can solve from there. Okay, so here's my calculation. And then when I plug this side over here into my calculator, I end up with 38.49, but it does say to round to the nearest year. So this is 38 years. 38 years what? 38 years past 1984. So then if I do 1984 plus 38, I get the year 2022. And that's my answer. Okay, so good luck with the rest of the homework. If you have questions about what we went through on this video, please let me know. But then I will talk to you in the next video. See you guys.